So in fact, I wish if we can work on a larger project instead of working with very small assignments, which is not, we need to, at the end, we need to have maybe a good project, so we can build a demo here. Maybe if someone wants to publish a paper or something, you can do it, right? So, this one? No, it should be fine, right?
Yeah.
Okay, so now we will start working with unlabeled data. When we are working with unlabeled data, it's unsupervised. So unsupervised, in fact, it's more important because there are lots of unsupervised data around us everywhere. So the problem, in fact, in getting data is to get supervised data. Because to get a supervised data, you need to label it. So you need to spend lots of time. So for example, working with those license plates, you need to label it, you need to collect your data first. You need to read the license plates, build your data set, and after that, training your model. But if you want to get unsupervised, you can just put a camera, for example, in the road, and it will just take images, millions of images. For example, in Staten Vivacen, they scan roads on Norway twice per year. So they have millions of kilometers, in fact, of images, millions. They do it twice per year. So they have fancy cars. Those cars has sensors and laser range scanners and the cameras, and they just scan all roads on Norway 2 times per year. All those images are unsupervised. So if you want to build a system for, we did a bachelor thesis here 2 years ago with the Staten Vivacen to use deep learning for predictive maintenance of roads. We need to build a system to quantify the quality of roads, for example. We need to predict remaining useful life of roads. So if it is unsupervised, we can just ask them in Staten Vivacen to give us access to the data, and you can just build your system and work. But it's a problem. We need someone to label the data. So we have been trying to identify cracks on roads. So we need someone to just take image by image and use this bounding box, both this bounding box, and say, okay, this one, it's severity, it's 0.8, 0.9, 0.6, and count in each image how many cracks we have. And at the end, we need to quantify it. We need to get a factor representing remaining useful life. So if it's too bad, in fact, we can just say, okay, it can't last for 2 years, for example. So we can say that remaining useful life is 0.3, 0.2. So we need to find a way to quantify it. So we need to get someone. In that project, we had 3 students working. So I've been spending lots of time in labeling all those images and preparing it for machine learning. And once they did it, they used the data for training a machine learning model. And the machine learning model, you can feed it with huge data set from every end. So they started with one place, in fact, from one city to another city, and they built the data set, they trained the model, and after that, they implemented it, and it was working very well. And they implemented that solution when we had the access to Microsoft Azure. So they deployed it quickly, in fact. They built API in Microsoft Azure, and they opened it for people to just upload any kind of images and get it clustered or classified or quantified. And at the end, we can build a map of Norway with colors. Roads has different colors according to the remaining useful life. So when you look into the map, you can say, okay, this part is bad, this part is good. If I'm traveling from here to Trondheim, maybe I can go from here, not from here, because lots of problems in that part. Lots of red areas, and I have to drive at slower speed and so on. So it was very good application. So lots of data unlabeled around us. If you want to build a system, so the field of machine learning, it's supervised against unsupervised. So the field of machine learning has 2 major branches: supervised learning and unsupervised learning. And supervised learning labels are available, which can be used to measure and improve the performance of some tasks through a cost function. So we need to have a cost function. We will use those labels as a teaching signal, and we will use it for evaluating the performance of my model. So the equation, remember, error equal half summation t minus y. T is the supervised signal. So this signal, we have this cost function or loss function. So E equal half summation t minus 1 square. So in fact, it's mean squared error, you can just say. So we can just say this is mean squared error. So this signal, in fact, we call it target feature or the teaching signal or label. So this one, it's a label. So if you have this one, we can go for supervised because now it's supervised. We try to minimize the difference between the target and the predicted. This one, it's a target, and this one, it's a predicted. So if you have this signal, if you have those, target labels, we can go for supervised. If you don't, you cannot go for supervised. We need to go for unsupervised. So in supervised learning, labels are available, which can be used to measure and improve the performance of our models. In unsupervised learning, labels are not available. We don't have any labels. So therefore, the task of the AI is not well defined, and the performance cannot be measured clearly. If I don't have those target signal, we cannot measure it. I cannot say that it works good or bad because I don't have any target signal, right? I don't have any teaching signal, or I cannot compare my performance to anything. So we need to use maybe our experience and so on. So unsupervised learning problem is less clearly defined than the supervised learning problem and harder to solve. It's more difficult, in fact, to solve, but if handled well, the solution is more powerful, right? Because we have a problem. For example, we can classify people who are sitting here, right? We can identify all persons. But if I build a machine learning for us, what will happen next year if we got new people? We will not be able to classify them. It will not be able to generalize to new cases, new classes, right? We are building a system to classify roads into the cracks in roads into 3 categories or 4 categories, for example. What will happen if we got something different? We don't know in the future. Something totally different from the 4 classes. If it is unsupervised, it will be able to handle this new class in the future. We will get a new class. It's unknown class or open set, data set or something. But if it is supervised, when it's supervised, it will be restricted only to the number of classes which we decided, right? So you have coins, for example, we have 4 coins on the way, for example, maybe 5, 10, 20, and correct, what else, 1? So we have 4 classes, and I build a system for these machines when you buy something from the machine because it classifies. Maybe according to the weight and the size, we can classify coins, correct? We don't know if they decided to make a new coin in the future. I need to retrain those supervised models because it will not be able to classify the new one. But if it is unsupervised, it will be able to handle it. In fact, it will get a new class, right? So for this coins problem, so I can classify coins by maybe weight and radius, for example, right? So when it's heavy and much bigger, well, maybe we'll have the 20 here, correct? If it is small in size and weight, maybe we will have 1 krona here, right? So it's unsupervised. It's easy to do it unsupervised using this weight and radius, correct? If you give it to a child, he will be able to classify it without any knowledge. He will just try to weigh it and the size. He will put big one here, smaller one here, maybe some other ones it will be located here, maybe for example 10 and 5 and so on. So it's an easy problem. If it is supervised, we need to decide how many clusters we have. We have 3 clusters. So we need to stick to those 3 clusters. If I got an outlier, it will not be able to classify it because we have only 3, right? But if it is unsupervised, no, it will be able to create a cluster for the new items. So it will be able, in fact, to generalize to new cases when it's unsupervised. So in fact, unsupervised, it's more powerful. But it needs some small help from us. After classifying it, we need to give it a label. So if I give to my machine, for example, a bag of coins, it will be able to classify it. But the machine will not understand what is the name of this class. So I need after training my model, I need to tell my machine, this one is 20 krona. I mean, this cluster is 20, this cluster is 10, this cluster is 1 krona. So now later on, when we deploy it, it will be able to count how much money we put in the machine, for example, right? Because it will know that the one which belongs to this one, it's 20, the one which belongs to this one, it's 10, this one is 1, for example. So it will be able to measure. If it is supervised, it must be restricted to the classes which we decided from the beginning. the data set, it will be restricted to the data set which we used for training it. But if it is unsupervised, it will be more powerful because it can discover something different in the future and it will be able to handle it. Unsupervised system is better than the supervised system at finding new pattern in the future data, making the unsupervised solution more nimble on a go-forward basis. So the solution here, it will be more, much better, in fact, compared to supervised learning. Why labels are so powerful? I mean, supervised learning in supervised learning AI trains on data where it measures its performance by a cost function by comparing its predicted image label with the true image using this equation, t-1. This is a target one, this is a predicted one. So we make those comparisons using this cost function or loss function. Labels guided the machine learning model or the AI agent by providing it with the error measure. So we use this error measure for adjusting the weights, correct? So this is a guiding signal, in fact. Because if I need to adjust the weights, so delta omega, it's just minus eta partial e by partial omega. So the error signal, it's the guiding signal, in fact. We will use this error signal to increase or decrease the weight value, right? According to this equation. The AI uses the error measure to improve the performance over time. Without such labels, the AI does not know how successful it is or not in correctly classifying images. I mean, using this error function, we will minimize it. So at the end, we can have this, error scale or error prediction error, for example, to measure the performance. However, the cost of manually labeling an image dataset is high. It's very expensive to build your dataset. So this is the cost which we have. So it's okay if we can label, but if you cannot label, what will happen? So we need to go for unsupervised learning. The best known image datasets have only thousands of labels, which might not enough for training some systems. There are some datasets, but it takes time, and there are lots of images around us. And I mean, according to the capacity of us, maybe we can just label a few thousand, for example, but not more. So those few thousand, it will not be enough for training deep learning, for example. If you will want to go for deep learning, we need thousands and millions of images. If you really need to build good systems. Supervised learning system will be very good at classifying images of object which has labels, but poor at classifying images of object which has no labels. If for example, AlexNet, for example, you trained it using millions of images to detect object in the image. If you trained it to detect this is a chair, this is a cup, this is a computer, it's fine. But if you have a new object in the image, it will not be able to classify it, right? Because it didn't. I mean, we didn't train the model for detecting this specific object in the image, right? But if it is unclassified, unsupervised, it will detect it and it will ask us to label it. And this is what has been done in Google. We have this album in Google, how do you call it? In Facebook even, or so you can just see that when you take some pictures and you put it in Google Drive, they have this, so it can put.
You can tag faces.
It tag faces, yes. So when you upload new images, for example, it tag all faces because it classifies it as a new person. But you just need to go by yourself and give him a label, correct? Did you try it in Facebook?
No.
When you upload an image, for example, it will tag all new faces. If the machine know you from before, it will give you a name or a label. If you are a new person for the machine, it will just wait for you to give it a label. So once you give it a label, it will take that person on all other images, and it will give him a label, the same label. So in unsupervised learning, in fact, we can tag people, we can classify that, okay, this is a new person, he is a new person or a new object, but we need someone to just give him a label. It's like this one. The machine will classify coins into different clusters, but we need someone to tell the machine, okay, this is 20 krona. If you told the machine that this one is 1 krona, for example, it will make calculations very wrong, right? People will pay less. So, right? But once it classifies it, you need to give it a label. As powerful as the supervised learning systems, they are limited at generalizing knowledge beyond the labeled items they have trained on. Since the majority of for-level data is unlabeled, with supervised learning, the ability of AI to expand its performance to never before seen examples is quite limited. supervised will be limited. In other words, supervised learning is great at solving narrow AI problems, but not so good at solving more ambitious, less clearly defined problems of the strong AI types. So in fact, when you use supervised learning, you can say that you go for weak AI, because when the problem is well defined, it's weak AI. We need a simple model to solve the specific problem at a very narrow domain, right? So it's very just narrow. I mean, machine learning is very good in solving very narrow problems. So for example, we can build a machine for classifying license plates on Norway, for example, because the license plates on Norway, it has a specific structure. If you will go to somewhere else, maybe it will be more complex, right? Classifying faces in North American people or whatever, if you want to expand it to more people, right? It's less defined the problem. When it's less defined the problem, we need to go for unsupervised learning. It will be much more powerful. So when you have a well-defined problem, you can just, when it's very well-defined, it will be weak AI, because we will use supervised learning for solving specific problem in a very narrow domain. But when it's less defined, you can just say it will be strong AI, because the problem is not well-defined, uncertainty is high. Maybe we will get some new clusters and new faces, new objects in the future. So in this case, we can go for unsupervised learning. Strengths and weaknesses of supervised and unsupervised. Supervised learning will, it's much better than unsupervised, in fact, learning at narrow defined tasks for which we have well-defined pattern or problem and don't change over time. I mean, if we have a problem faces which does not change, we classify items. For example, we had a master thesis or a bachelor thesis in fish, classifying fish in a company, for example. Right? So if you are expecting that all fish will be salmon, for example, it will be okay. But in the future, if you will get a different type or a different species, for example, which the machine will not be able to classify it. So in this case, it was better to go for unsupervised, because all species will be classified as some defined classes, and the one which we just got now, which is different, it will be classified as a third class, which is unknown. So the machine will tell me that we have a different cluster here, and you need to go and just check it and give it a label, for example. So the unsupervised, it's more dynamic, in fact, and it can be extended for solving more complex problems in the future. Unsupervised will truly shine for problems where patterns are unknown or constantly changing over time, which we don't have sufficient large label data set for it. So if you have, it's just, now you know the story. I mean, if you have features which are changing over time, for example, so in this case, you can go for unsupervised learning. So I can train a model to recognize myself in the moment. Maybe after 5 years, it will not be able to recognize me, correct? So because I trained my model for well-defined problem, but I didn't consider that there are some features which will change over time. So after some time, it will not be able to classify you. I trained a model to open the door just without glasses, and I am wearing a glass. It will not be able to classify me, right? It will not be able to recognize me, because now I didn't consider that there are some features which can change over time, for example, or
will you then take the new label and mark it as one of the ones that you have from the course?
Yeah, for example, so you can just give it a new label, for example, the machine will discover this person, or you need to retrain your model using the new dataset, right? So, and this is the problem, for example, if we building a system for face recognition and you trained it with images which has been taken in daytime, and now we need to test it at nighttime, and it's not working at nighttime because, anyway, so the unsupervised will be more powerful in such cases, in fact. But it needs small, just intervention from the people. It will classify people, it will create a new cluster. So we need someone to go and just check, okay, this is a new cluster. You need to give it a label, for example. So now it will work fine. Instead of being guided by labels, unsupervised learning works by learning the underlying structure of the data it has been trained on. After the initial training, if the unsupervised learning finds images that don't belong to any of the labeled groups, it will create a separate group for the unclassified image, triggering a human, so asking a human to label the new yet to be labeled groups of images. And this is what Google is doing, in fact. So when you upload an image, it will tag people. If he is a new person, it will just give him a tag or a bounding box, and you need to go and give it a tag or a label, right? So this is how it works. And if you just said, okay, because it will classify him, it would cluster the new person on all images, right? So once you give it a label, it will be able to recognize him in the new images and give him a tag and maybe trigger him or send him, like in Facebook, for example, right? So it's all those techniques are unsupervised learning. So examples of supervised algorithms, simple one. Artificial neural network, we know it, right? So now we have some inputs, we have some structure for the neural network, we have some outputs. We use this equation for adjusting the weights. So this is supervised. Another example, it's called KNN, key nearest neighborhood. Key nearest neighborhood, right? Did you know about it?
Yeah, it's you make clusters and you define how many clusters you want to have, and then it defines a radius and tries to figure out depending on.
Yeah. So it's exactly So in fact, as you mentioned, I have a data set, but we need some knowledge from the domain expert. So for example, Iris data set. Imagine that I'm using X1 and X2. We just have two features. And I know that those dataset has 3 clusters. We know, domain expert. I know that this dataset has 3 clusters. So you can just say, okay, please build the 3 clusters. I mean, you need to define how many clusters. So it will pick 3 data points as centers, right? And it will try to, or it's not like this. In fact, it calculates the Euclidean distance. So
that is k-means.
KNN.
K-means. That's
K-means.
the one that you were describing.
Key means not key means the clustering. Key nearest neighborhood.
Yes, but the one that you were describing was k-means, I think. It takes 3 points.
No, yeah, this is key means the clustering. But KNN,
Is different.
we need to check how close the data point to how many candidates or nearest neighbors, how many neighbors. So for example, I have my data point like this one, and I got a new data point here. I have here 2 classes. We have the triangle, it's 1 class, and the circle, it's another class. And I got a new data point. So I will just, I will see how many is the closest key nearest neighbors. If I select k equal 1, for example. So I will calculate the distance between all those ones, right? This is the problem here, calculation, lots of calculation, because I need to calculate the distance between the new candidate and all other data points. And I will check what is the nationality of the nearest neighbor. If k equal 1, so I will check. Oh, this is the closest to me, right? This one. This is new data point. So I will check if k equal 1. I will check about the class. What is the cluster? What is the class of this one? Is it triangle? If he is triangle, I will be a triangle. If he is a circle, I will be a circle, right? If you want to make it more maybe robust, you say, okay, I will check for k equals 3. So I will expand my circle, my radius, for example, and I will check the nationality or the classes of the nearest 3 neighbors. So I will check, okay, this one, it's a triangle, but those 2 are circles. So I will vote for it. It's like voting. So I see 2 circles and 1 triangle. So probability is that a circle, it's more than probability of being a circle, correct? So in this case, I will be classified as a circle, not as a triangle. So this is the key nearest neighborhood. So it's a supervised, correct? Because I'm using the target classes labels. I'm using the labels here, in fact, because this one it's labeled as a triangle. This one it's labeled as a circle. So we are using it's supervised because we have labels. Labels are included here, right? And the k, it's a factor which we need to decide. It's integer number, and this integer number we need to decide it. Is it 1, 2, 3, 4, 5? Right. So according to the performance. So it's also hyperparameter which you need to check. So in fact, is this one it's supervised because we have the labels with us, and I will check the distance between myself and the k nearest neighbors, for example, and we will vote which class should we belong to, right? So KNN looks at K number, which is an integer number of nearest labeled points or neighbors, and the vote in how to label a new point. We need to have this voting. When K equal 1, the algorithm is known as the nearest neighbor algorithm. Nearest neighbor, only one neighbor algorithm. By default, KNN uses Euclidean distance to measure what is the closest. We need to calculate the Euclidean distance and sort it. It overfits the data when K is very low, correct? It will be just overfitting because I'm just looking to the nearest one, right? Because maybe one is close to me who is, but the other two, for example, they are from another class or the other 5. So maybe I am in the middle of a cluster 1, but the closest one to me is an outlier, for example. So I will classify myself as the other one. So it will overfit. It will go into micro details between neighbors. So when K is very small, it can overfit your data set. It overfits the data when K is very low, and underfit the data when K is set to a very large value. KNN is a lazy algorithm, meaning it doesn't need any training data point for model generation. We need to keep all data points with us all the time, right? This is the problem here. So they call it a lazy algorithm. It didn't learn anything, in fact. It's just a calculation. Nearest neighbors, for example. So we don't have a model at the end. So they call it a lazy model or lazy algorithm. KNN is classifying a new data point. It needs more time to scan all data points. I need to scan all data points and more memory to store and sort all data points. This is the problem. Computational cost is very high here because I need to keep all data points with me all the time. Because I have a bag on my back, for example, and I have all data points with me all the time. And if I got a new one, I need to measure the distance between this one and all data points and just check the nearest K candidates or examples and just vote for what clusters I should belong to. So I need to keep all data points all the time with me, right? So it's computational cost and memory cost. Classifying a new data point, it needs more time to scan all data points and the more memory to store and sort all data points. KNN performs poorly when the number of observations and features grow and it becomes computationally inefficient. So if you have 10 features, it will be really very complex. But when it's 2 features, it's easy even to visualize and easy to understand how it works. But when it's more complex, it will be an inefficient algorithm. Number of neighbors, K, is hyperparameter that you need to choose at the time of model building. KNN is used to recommend, predict what the user will like. For example, in Facebook Friends, Google Search, Amazon potential shopping list, and so on. It's KNN effect, right? Because they know in Facebook, for example, when it recommend a friend to you, for example, how can we know it? So we have lots of features. We are from the same region, we have the same education, right? We are posting the same number each day, for example, right? We love, both of us, politics, for example. So they try to find the nearest neighbors to my profile, for example. So they have profiles of many people. Each profile is defined by number of features, right? We are both at NTNU working in the same place. Both are on the same age range, for example, right? Both of us like football, correct? So in this case, they can find nearest neighbor to us and recommend the new friends in Facebook, for example. You know, in LinkedIn, sometimes someone is popping up because this one is close to us. And when you check him, for example, you can see, yes, we are working in the same area or have the same hobbies and so on. So they use KNN for doing this. But it's, yes, recommendation system in Amazon, for example, when you buy a book in a machine learning, the next week you will get a recommendation for the same book. So they got a new title. They use some keywords for classifying books, for example. So when you buy a book, they build a profile for you, right? And you know that you like this area. So when they have a similar book, so they will recommend it to you. So they try to measure the Euclidean distance between my profile or my reading list, for example, and new titles. So they can recommend this one to you, right? So, and also in Google search, for example, when we search for many things, because usually, we search maybe for technology, for computers and so on. So they make it, more handy for you, more easy for you so they can recommend things for you. So this algorithm KNN, it's an example of supervised learning, and it's supervised because we need to keep those labels, right? And when you have an example in the future, I have my data set, I need to keep it with me. This is a problem. And this is a problem with privacy as well, correct? Because if you are working with customers from the bank, I need to keep all information of those customers with us, right? Which is a big problem. Because you are not training a model. If you are working with feed-forward neural network, I will train my model and I will run away, right? You have your weights, you have your model which has been trained, use your data, I don't need the data anymore. Correct? So it's I mean, using feed-forward, it's more simple, and it's okay because I don't need to keep all data with me all time. But in case of KNN, you need to keep all those data with you all time. And then when you have a new example, we will measure the distance between this one and this one, 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 right? And I will sort them in descending order, correct? And I will check how many K. If K is equal 3, I will select the nationality, for example, of those candidates, the nearest K values to me, and I will check and I will vote if I should be blue or red, for example, right? So this is KNN.
So it means high computational
Cost.
Yeah.
Yes, very high computational cost and the memory cost also.
I just want to ask you, the KNN, are there some algorithms that can be used only for unsupervised learning, or are there algorithms that can be used for both supervised and non-supervised?
Key means the clustering, for example, it's unsupervised. So we will take some examples for unsupervised, but this is an example for supervised learning.
Supervised.
This one supervised. KNN, it's supervised. It's similar to neural network, but neural network it's less problematic in terms of privacy and the data, GDPR and stuff like this. But in case of KNN, it's a problem because I need to keep all data points with me because we don't build a model. In fact, the model here, it's a lazy model. It's a very simple one. I don't have any weights, don't have any bias, don't have any equations. No, I need to keep all my data sets with me, and I just calculate the distance from my point to the data sets, sort them, right? Do these calculations all time, and just vote for class and just classify, right? If we have 3 classes, if we have 4 classes, so it's computationally expensive, especially when you have lots of features. Imagine you have 100 features, you need to calculate the distance, how the space will look like. It will be very complex. So it will take too much time for each point. But in case of neural network, once I trained my model, I will feed the image and it will be classified, correct? So in our feed-forward neural network, if we do it for face recognition, once I trained it with millions and millions of images, now we are happy. I have my model, I have my weights. I will just take the image, feed it to my model, and it will be classified. So neural network, it's good for parallel computations, and it's more quick. If I need to build an autonomous car, for example, I need to take the images in front of me if I'm driving at 100 kilometers per hour, and I just need to classify quickly, right? This is road, this is trees, this is quickly. But imagine if I'm doing the same using KNN, how much time we need, right? How many milliseconds we need to classify?
We don't have the time to compute all the time.
Yes, we don't have this time. So I need to train, prepare the model, and just feed it with real-time images, and we'll just classify it, right? But in case of KNN, it's impossible to use this algorithm for an application which is faster processing time. So how KNN works, I just explained it. Suppose B1 is a point of which a label we need to predict a label for this point, for example. First, you find the K closest points to B1. We need to find the K. How can we find the K closest? Using Euclidean distance. We will calculate the distance between this point and all other points. Sort them in descending order and find K closest points to B1, and then classify points by majority vote of its K neighbors. So I will check the majority. If the majority is class 1, this one will be class 1. If it is class 2, it will be class 2. 3, 3. If it is 50-50, so we need to decide, right? If it is 50-50, we need to decide. It could be 1, for example. That means the first one which pops up, for example. Each object votes for their class, and the class with the most votes is taken as the prediction. For finding the closest similar points, you find the distance between points using distance measure. You can use Euclidean distance, Hamming distance, Manhattan distance. So there are many ways for, of course, there will be some difference between those, but I mean, it has some basic steps. Calculate the distance first, find the closest neighbors, vote for labels. Very simple, right? But as you can see here, to calculate the distance, we need to keep all data points with us all time. Maybe you can develop a new version which require less. I don't know. I mean, you need to check it. Maybe someone can just try to develop those algorithms to need less distance. But the problem here, we don't have a model, right? It's an approach, in fact. We don't have any models. So you need to keep all your data points with you all time, which is heavy and it's really very complex. So imagine those data points. If I build a system for patients in a hospital, we cannot keep those data points with us. No one will agree, in fact, right? To keep his information in your computer because you have KNN. But it's okay to use feedforward, because feedforward, I will train it, and after that, we will delete the data. I don't need to keep the data, right? You can go for stochastic gradient descent for online learning. If I got a data point in the future, I will just use it for retraining the model, but I will not keep any data points in my computer. This is very important. So this is an example. So we calculate the distance. We will sort them in descending order. We will check how many Ks, I mean the nationality or the clusters of the key nearest to my data point, and we will just vote for it, and we will give it a label according to the majority of votes. Yes, I implemented it, but it's simple. You know, we have it in sklearn K-neighbors classifier. We have it in K. If you want to implement it step by step, you can do it, right? Because we know we just need to calculate the gradient distance, sort them in descending order, and just find the majority of votes, right? So if you want to implement it step by step, it should be possible. But I imported it here from sklearn. We have a neighbors classifier. So it's KNN equals this one, and I just selected 5, K equal 5, right? And it's supervised. When it's supervised, we don't need to specify number of clusters, because anyway, number of clusters are provided in my data. So I will use iris dataset. So I will fit the model, and I will predict for a new data point. So I divided my data points, in fact, into a training and test set. I used the training set, X-train, Y-train, because it's supervised for building our model. Imagine it's building our model, but we are not building any models, in fact, right? And now we are predicting, and this is the decision boundaries for. I run it 3 times. I didn't specify any random seeds, so I tested it 3 times. So each time I'm getting a different boundary conditions, decision boundaries. So now I have one cluster here, one cluster in the middle, and one cluster here. How can you draw this one? Simple, just enumerate or just get x1 and x2 and create a grid and send it to the model. So it will cluster it into 3 clusters. So for example, if you have a point here, for example, and the K equal 5, so I will calculate the distance between all my data points. So chuk. So it will belong to this one. Here also in the middle here, it will be closer to this one compared to this one. Any point here, it will be closer to this one. It's more complex here, right? Because if I have a data point here, we will find the nearest 5. So maybe sometimes it will be here, sometimes it will be here. So the algorithm is very simple. And if you want to implement it from sklearn, it will be just simple as this one. Yeah. So maybe it will be more complex here. You can try it with different K values. For example, K equal 1. When K is low, just remember when K is low, it will overfit your data set. When K is too large, it will underfit your data points, right?
Sorry, Ibrahim, if it is the same data, the same distance, why are we getting different results every time? The distance doesn't change.
Yes, you are right. So what is okay? Yes, it's different because when dividing the data into training and testing, I used a function which shuffle.
Okay. So
this
different
is the
data.
only, yeah, correct.
So different data sets we have.
Different the training set and the testing set. Because I used this function, split, train, test, split, and this one, it shuffles the data each time. So if we didn't specify the random seed, you will get different set each time.
Okay, makes sense.
So unsupervised, it's smart, but the most important application, in fact, for dimensionality reduction, we studied BCA before, principal component analysis. It's unsupervised because we are working with features. We are not working with any teaching signal, correct? We have a set of features. I have 20 features, but I don't work with those 20 features. I need to select the most important features. Maybe I need to select 3, for example, correct? 2, because if I select the most important 2, I can visualize my data point in 2-dimensional space, for example, right? So we use BCA for dimensionality reduction. Clustering, we can use k-means clustering. So this is k-means, correct? We need to select centers or centroids. And after that, I have a data, for example, iris dataset. I will apply it to iris dataset, k-means clustering, and we will see the difference. So you need a domain expert who can say, okay, those data came from 3 classes. Because I need someone to help me, in fact, and to tell me how many classes we need to get. If it is for coins, we know that in Norway, for example, we have 4 different coins. So in this case, K will be 4, right? We will start with 4 centroids and we will try to cluster. If you will set 5, it will make a problem for my model because it will not be realistic, in fact, right? So feature extraction, autoencoders are beautiful, because we can use autoencoders, in fact, for dimensionality reduction as well, right? So do you remember last year we had this, we had an exam last year, so I was asking students, in fact, how can we implement BCA using autoencoder, right? So we can use this autoencoder for dimensionality reduction and denoising, in fact, right? Denoising, if you have some noise in the data, I can build an autoencoder to remove the noise. Because sometimes, for example, you have a sensor and the sensor is measuring some signals. There are some uncertainty and noise, for example. I need to get rid of those noise. So I can build an autoencoder to remove those noises. You build a machine learning for face recognition. I need it to work in all different lighting conditions, right? So how can we fix this? Maybe using autoencoder to remove noise, to remove stuff like this. And the unsupervised pre-training. So dimensionality reduction, we talked about this dimensionality reduction using BCA before. So it's unsupervised learning. You try to learn the underlying structure of a data set that does not have any labels because we are working with features. So we are not touching labels. We don't need labels. We are working only with features. Dimensionality reduction algorithm, it projects the high dimensional input data to a low dimensional space. I have all my features in 10 dimensional space, and I want to reduce it into 3-dimensional space, for example. I need to reduce the dimension of the data. I need to get the most powerful features, and at the same time, I need to reduce it so I can visualize it, and I can make it easy for my model. Because remember, number of inputs for any models will be the number of features. And when the number of features is large, the model will be more complex. And when it's complex, it might overfit your data. So one way to simplify this is to reduce the dimension of your data set. So filtering out not so relevant features. We need to filter out not so relevant features, because sometimes when you are working with real problem in banking systems, for example, you are getting too much features, might be it's redundant or it's just does not have any new information for us. So we need to get the most important features for building our model. And keeping as much as of the interesting ones as possible. I need to keep only the most important ones and the most important interesting ones. Dimensionality reduction allows AI to be more efficient in solving large scale and computationally expensive problems because we will reduce the size of the features, often involving images, videos, speech, and text. We need to get the most, because imagine, in MNIST data set, the size of the image was 28 times 28, which is 874. Correct? It's a huge 784 or 874.
Virtual.
Yeah.
784.
784. So 784, it's too much. And the image is 28 times 28 pixels. So it's very small, but the problem is really very complex. So imagine that you are working with an image which is 512 times 512. Right? 4K images. What will be the situation? And when it's 3 channels, it's RGB image. it will be very, very complex, right? So it's important to try to reduce the dimension of the features to make your problem can be handled easily. PCA identifies which features out of the full set of features are most important in explaining the variability in the data set and filter out the features that are less useful in explaining the data set. So we just try to find the most important features which are explaining. But PCA, we had many examples before in PCA, correct? We used it with 2 weeks ago, I guess. We used it with MNIST dataset. But if you need more examples, we can get more examples. So we will go to k-means clustering. K-means clustering, it's once we have reduced the set of original features to a smaller and more manageable set, we can find interesting pattern by grouping similar. It's for classifying or clustering. With k-means clustering, we specify the number of desired cluster k. We need to specify k. So we shall say k equals 3, k equals 4. How can we decide this? It's by a domain expert. So we're just visualizing your data. We need to visualize the data first to see how many clusters we have, right? And after that, we can decide, okay, it looks like we have 3, we have 4. Or from a domain expert, if you are working with IRIS dataset, we have 3 clusters. If we are working with MNIST dataset, we have 10 clusters. So we need to specify how many clusters. So in fact, you can use k-means clustering for MNIST. You can try it. Can we classify each image into its correct cluster, for example, if it is 0, 1, 2, 3, 4, and so on? To speed up this clustering process, k-means randomly assigns each observation to one of the key clusters. It will pick key examples as centroids at the beginning. And then beginning to reassign these observations to minimize the Euclidean distance between each observation and the cluster center point or centroid. For example, I will have a center point, right? I will pick one data point as a centroid. And after that, I will pick the second data point, and the centroid will move closer to the second one, which is closest to it. So it will be like this one. I will, for example, in MNIST dataset, I will pick 3 examples as centroids at the beginning. So this one will be a centroid. This one will be a centroid. Maybe this one will be a centroid. Because we have 3 clusters. So the number of centroids will be the number of clusters. And when we are getting a new data point, imagine that I got a data point here. It's the same. We will calculate the Euclidean distance between this one and all the 3 centroids. Okay, this one is closer to this one, right? So it will be close. So this one will be attached to this one. So I will classify this one as a rectangle because it's closer to this one. And I will update the centroid. The centroid was here at that point. Now it will be at the middle. So this is a new centroid for this one. Next time, I got a new example. Imagine, not here, I got a new example here, right? Data point here. Okay, this data point, I will calculate the distance between this one, the centroid, the centroid, the centroid. This point, it's closer to this one, right? So in this case, this one will be classified as rectangle, and we will update the centroid. Now the centroid will become here, and so on.
But at the beginning, we have to label 3 data.
Yes, we need to decide k, because I said that we have k equal, you need to decide how many clusters you want. So we need to say k equals 3, for example. If k equals 3, I need to pick 3 data points. And this is a problem, by the way, also here, picking which is 3 points. What will happen if the 3 points are in one cluster? This is a problem in k-means clustering, in fact. Right? So this is a problem here, which, because we hope that we will select 3 examples as centroids from the whole distribution. I mean, with each are independent or long distance. So this is a research point here, in fact, because what will happen if I selected the 3 centroids here, right? So it will overfit. It will overfit or underfit the data points. It will be a problem, right? So therefore we update the centroid each time to try to get 3 different centroids away from each other. So we select 3 data points as centroids because we selected k equals 3. Each one will be a cluster, but we don't give it a label. You need to do it at the end, right? But you can just imagine this is blue one, this is green one, this is red one. And we will start with the first data points. We will measure the distance between this data point and the 3 centroids. We will attach this one to the closest one, and we will update the centroid. We will go to the second one, and so on until we finish the data points. Right? So at the end, we will have a centroid for one cluster, a centroid for another cluster, a centroid for a third cluster. The problem here, it's in the random seed, which 3 points which we will select. Each time you will get different solution, but we should converge to almost the same solution. So as a result, the difference of k-means, each with a randomized start, will result in slightly different clustering assignments of the observations. So each time when you run it, each time you will get different assignments, slightly different, right? From these different runs, we can choose the one that has best separation, defined as the lowest total sum of within cluster variations. So you need to run this algorithm, in fact, several times, and you just need to select the one which looks better, looks fit, where we have different separations of clusters, right? So he mentioned here, it's the one which is defined with the lowest total sum of within cluster variations. We need to select the one which with less variation to stick to each other. A cluster which has really an identity and looks like a cluster. So we try to minimize the variations in each cluster. You need to select the one which with less variations, because it will look like as a cluster. So I did that also for this example. Maybe it was better if we, so at the end we have also one cluster here, and another cluster here. We have some overlap here, right? Maybe the centroid, it was better also to plot the centroid, right? At the beginning, the centroid will be a data point, but at the end it will be a centroid, not a data point. So it will be smart also if you can do this one and plot the centroid, how the centroid moves, right? Because the centroid will start with a data point and it will converge to some place here. So if you can plot it, it will be very good. I did that before, in fact, maybe last year or the year before in MATLAB. So we can just make it, you can implement the algorithm step by step and plot the centroid to know how it moves, how it converges.
On the object, you can use the k-means dot cluster underscore centers underscore. Then you will get the parameters for each centroid.
Can you? So we can get the parameters of.
Yeah, you can just call this on your
centers.
Object, just clusters and centers, and then you will get the parameters, and then you can plot it.
Yeah, very good, very good. So it will be very good. I need to add it. Can you send it to me by email, please?
Yeah.
So I can update this one, so we can plot the centroids, because we will have 3 columns, in fact, one for each centroid, and you will start by some point. We pick it by random, and it will expand, and you can plot it. So you can find the center of the cluster. So now we have 3 centers. This algorithm is very smart, in fact, because at the end, you will have 3 centers. If I got a new point in the future, we will just measure the distance between this point and the 3 centers. And we will assign it to the closest one, right? So imagine it's coins, and I did this one for the coins. Now I have a center here, and a center point here, and a center point here. And I got a new coin, which I don't know. We will measure the center width, and I will calculate the distance between the new coin and the 3 centers. Imagine I got a data point here. So I will just calculate the distance between this one, and this one. And I will assign it to the closest one. If this one is closer to this one, I will just say, okay, this one is 20 krona, right? So from this algorithm, we will get 3 values, or k values, k centroids. So this algorithm, it's much better, in fact, than KNN, because KNN we need to keep all data all times. No, this one will train. The result here will be k values, k centroids. And if you got a data point in the future, you want to classify it, we will measure the distance between the new point and the 3 centroids, and we will assign it to the cluster of the closest one.
In the testing, it doesn't update the weight. For example, after assigning the new data to one of the clusters, it doesn't update the centroid.
No, it updates the centroid.
Also
In the training,
training.
yes, it updates.
Yeah, but in the testing, it will not do it again.
No, in the testing part, testing. It's a similar in neural network. In neural network, we are not updating in testing, correct?
Okay, so we will stop over there.
No, and just if I'm dividing my data here into a training and testing, it's just for testing the accuracy of the model, right? But you will get key values because it's a key. Key means the clustering. Key means we will get key means at the end. Key means clusters. We will get key values, key centroids. So you will have those three values, and if you got any point in the future, you just measure the distance. Okay, this one will be this, right? So you will have key values at the end. I got the code from. I will update it so we can plot the centroids. So in fact here, I used also Iris data set and I split it into a training and testing. But remember this one, it's unsupervised. So we're not using Y, right? We're not using it, we're just using X values because it's unsupervised, correct? I just used this data set because we need to test the accuracy of the algorithm, but it's not, it's unsupervised. We are using only X train and X test, for example, or X train. So the key means, we can get also key means from sklearn, and in here we need to, define number of clusters, maximum number of iterations. This algorithm, in fact, for calculating, Euclidean distance, when it's automatic, it's a Euclidean distance. If you need another distance measure, you can specify it here. Random state. And I used, you see, I used only X train because it's unsupervised. We are not using X and Y. In feed-forward neural network, we fit the model using X and Y. Here we use only X, right? And after that, I'm using X test for predicting, Y predict, and I used Y predict and Y predict and Y test for testing the accuracy because my data set is supervised, it's labeled. So I'm just using it so the accuracy was 91%, right? For Iris data set. So the accuracy is very good. And this is the decision boundary. Also the decision boundary, I need to create a grid of X values of my features, and I send those values to my model, and my model will classify it into one of the three classes. So imagine you have a point here, maybe the center is here. So you will calculate the distance. It's closer to this one or this one or this centroid. Color, this one it's Virginica, I guess, right? We have three classes. So we need someone to go and label it. It's similar to Google when it, tag persons and images, we need to go and just label him, give him a label. So automatically later on it will be able to, okay, and it's in a spam filter in your email also. So when you have an email which is a spam, in fact, this email, it has some features. So we can get some features and text something from the email address, for example. And if you just click, okay, this one is a spam, it will go automatically next time to trash box or, correct? You will not get it in your mailbox because you labeled it as a spam. So it's unsupervised. Because when you are getting an email, it has some features, right? On my model, it's unsupervised. It's not supervised, it's unsupervised. So I need by myself to go and say, okay, this one, it's a spam. Next time I will not get it. Correct? Yes. Okay, should we go for autoencoder? We can go for autoencoder and you can play with it at home, right? Mm-hmm. So the autoencoder, it's a feed-forward neural network, in fact, right? And it consists of two parts. One part, it's encoder and decoder, right? And it's unsupervised learning because the input is X, the output also is X. It's not X and Y, but it's X and X. So if you build a neural network, which is symmetric, and the input is X and the output is X, number of outputs equal to the number of inputs. It's an encoder, autoencoder. And the one in the middle here, we call it bottleneck, right? Bottleneck. I will train it, so the input is 2. If it is with MNIST data set, the input is 2 and the output is 2. if I trained this model like this one, right? I can just use the encoder later after training it. I can take that part and use it for dimensionality reduction. Correct? Right? Dimensionality reduction. I have 784, 786, 84. Sorry, I have. It's Alzheimer. So it's 784 inputs. You can just decide the size of the bottleneck. How many features do you want to keep? If you said I want to keep 20, the most important 20 features. So just decide, okay, the size of the bottleneck here will be 20. So it will be, if it is one layer, so the input will be 784, 20, 20, 784. And I will train my model, right, to reduce the error between the output and the predicted output and the label. Imagine that it's a label, but it's not a label. In fact, it's the input. So after training this autoencoder, I can extract that part and use this one as a PCA, principal component analysis, or as an encoder. So now it will encode all those input images into a small set or a subset of features. Now I can use a subset of features for classifying it. So now I can use this one because after training this one, I can just use this one as like a principal component analysis. So reducing it into a subset of features. And I can use this one for just, so this is two. In fact, white is one and black is 0, correct? So it will be just, maybe this one, it's 10 times, 5 times 2, it's 10 features. So it will be 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, for example. It will be something like this one, or a float number, or anything. And we use this one also in fact in text, because also in text we need, when we have a large dictionary, for example, I need to reduce it into. We will talk about it later on. We can just talk about autoencoder today. So this is the autoencoder. So the autoencoder, it's feed-forward neural network. It's a specific type of feed-forward neural network where the input is the same as the output. Input is the same as the output. They compress the input into a lower dimensional code and then reconstruct the output from this representation. I mean, we will encode it into this lower dimensional, and after that we will reconstruct it one more time. We did that in PCA as well. So we can reconstruct the image using a small set of images, a small set of features, right? The code is a compact summary or compression of the input. We use it for compressing because also today, when you have lots of images, it's very expensive to store this 4K as a 4K. It will take big memory. So we can compress it. And when you compress it, you can transmit it to someone else. It will be much easier to transmit compressed data, right? And after that, he can reconstruct it. So we can use something similar. Compressed data, transmit it. It will be much easy, cheaper. And after that, you can reconstruct it. It will help us to reduce the bandwidths and correct. So it will be more efficient for data transmission. Storing, if you want to store those data in computer, in a certain Vivason, they scan the roads 2 times per year. How can they store all those data? Maybe they can compress those data, store it into a lower memory size. So now it's possible to keep data for 10 years, 20 years, 50 years, and so on, right? An autoencoder consists of 3 components: encoder, the code, which we will get here, and the decoder. The encoder compresses the input and produces the code. The decoder then reconstructs the input only using this code. So we compress and we reconstruct. Compress, reconstruct. Autoencoder learn new representations of the original input data via the encoder to minimize the reconstruction error. We will get some error here. It's not prediction error. When it's feed-forward the neural network, we can say it's prediction error. No, when it's encoder, we can just call it reconstruction error. We try to minimize the reconstruction error, the difference between the predicted and the actual. Autoencoders are mainly dimensionality reduction or compression algorithm. We can use it for compression or dimensionality reduction. It's data specific, which means autoencoders are only able to compress data similar to what they have been trained on. So if I'm working with MNIST, it should be working for MNIST. If I will try it for Olfiti, do you know Olfiti dataset for face recognition? Maybe it will not work, right? Because it's a data-driven one. because the weight values here, we trained this one for this set of images. So it's not transfer learning, but we need to test this one also. So we cannot expect an autoencoder trained on handwritten digits to compress landscape photos, right? It will not work because we trained this one for this data from this area. It's lossy, which means the output of the autoencoder will not be exactly the same as the input. It will be a close but degraded representation. It's the same in PCA also. When we reconstruct images using a small set of features, it's lossy reconstructed image, in fact. It's not exactly the same, but it's a little different. It's unsupervised to train an autoencoder. We just throw the raw input data at it. You don't need explicit labels to train on. In fact, it's like he just try to just fool us, in fact, because it looks like supervised. Because we have inputs, we have outputs, but because we are using only the features, we call it unsupervised, right? But technically, it's supervised, right?
I just want to ask you, concerning the PCA, what was the difference? Because
PCA,
yeah.
PCA, it's based on statistical tools. We calculate the eigenvector, right, and the eigenvalues.
To refresh my mind, I will look at it.
Yes, and I have a presentation, in fact, from last year, which I explained it in detail. So I will put it in Blackboard, or maybe I can present it one day. So I mean, PCA, it's more statistical approach, right? We calculate Euclidean eigenvectors, and all principal components are perpendicular to each other. So we select the first one in the direction of largest variation of the data, and the second one will be perpendicular, and we calculate variance. So it's a statistical tool, and so I can share something with you or in Blackboard for PCA. Yeah, I didn't go into details because maybe I thought that we need to be more implementing and
Yeah.
So I implemented here autoencoder for Iris dataset. So just I implemented. You can go for this code. It's autoencoder number 1, autoencoder 1 for NNEST. And there's a code here. So I use the Keras. Keras is fantastic. We need to use Keras. We need to use it as much as we can. But you can just do any. You can go for sklearn if you want. But here it's just easy. So I use the sequential API. I mean, you know, in Keras you can go for sequential or you can go for a model. So I use the sequential because it's more I mean, broad, more popular. And I use the two layers, right? 2 layers. So the first layer has the dimension of the input is 784, and it has 32 units. So I will plot it here. I don't know if people are online, they can they watch us or they, can you say something, please, if you are following us? So the autoencoder will be like this one. So in the middle here, I will have 32 nodes. No, okay. Yes, it's. I mean, it's one layer. I mean, this. So the encoder layer, I will call it the encoder layer. It will have 32. So it's 1, 2, 3 until 32. Okay. And how many inputs? So it's x1, x2, x3 until x784. So this is the input layer. So the input layer will have this size. Number of features will be the number of pixels, correct? This is the bottleneck. So we will have those connections. This one will be connected to all. Correct? We will just do it like this one. So it will be like this one, right? So this is the input layer. So the size of the input layer will be 784. 784 because in MNIST dataset we have 784 pixels, right? And the pixel value it's 0 and 1, right? So this is a bottleneck. which has 32 features or 32 units. And after that, the output layer will be so the size of this output layer will be 1, 2, 3, 784. Right? Connect. Just make all those connections. So can you find how many weights here? It will be like this one. So this is my autoencoder. So it consists of 2 layers. The first layer, we call it encoder. This one is encoder. And this layer, we will call it decoder. The one in the middle here, it will be the code. This is the code, or the bottleneck, correct? So now the input will be X, which is the image. The output will be X, which is the image, the same image. And we will train it using, for example, SCDG, for example, SCGD, for example. We will try to minimize the reconstruction error. The error between the input and the output, or the output and the target, which is the input, right? So once we train this model, can you, how many weights we have here? Can you calculate it? How many weights?
784.
784. So the input layer here, the first one here is the encoder. It will be 784 times 32. 32.
And the other side is the same.
Is it correct?
Bias.
Plus 32. Yes, plus 32. Okay, so this is the number of weights of the encoder. For the decoder, it will be the same, correct? But here it will be 32 times 784 plus 784. So this is the number of parameters. And now we just use any algorithm, any optimizer for training it. So in this case, after training this one, I can just extract this one. I can just use this one for dimensionality reduction. Once we train this model, I can just use the first layer as a dimensionality reduction, correct? Because I can, if I will use this one, when we apply an image, which is 784 pixels, I will get a vector of 32 values only representing this image, right? And in fact, I can use these 32 values for reconstruct the image one more time, if you want. I can use those 32 values for reconstructing the image. So now I can use this autoencoder for dimensionality reduction. So if we go here, I used this dense layer, and it has 32 units. I will use linear function. You can just try any functions. You can use RLN, rectified linear unit, RLEU, for example. This is a dimension of the input, and I give it an encoder layer. This one is a decoder layer. We don't need to specify, in fact, the input dimension, because the input dimension will come from here. We need to specify the number of units, 784, and I used this algorithm mean squared error accuracy, and I trained it. So finally, I can have this structure. So this is the dimension of input, encoder layer. This is the input layer, which has nothing. In fact, it's nothing. Just ignore this one. So this is the encoder layer. So the encoder layer, it will be 784 times 32. And the decoder layer, it will be 32 times 784. And the encoder will look like this one. Number of parameters, it will be this number, right? This one, it's much larger than this one, correct? Because we plus 784, but this one, it's plus 32, right? So this one, it's higher than this one. And I just trained it for 10 epochs, and I got this solution, and we can, for training it, do you see? For training, and the input is X and the output is X. Correct? So we are training it, it's similar to KNN. When we have been testing, we just train it using X. So we train it using X, and input X will be X, Y will be the same X, right? So now this is the it's just, I mean, there are some, if you want to extract the part for dimensionality reduction, you can just build a model, in fact. So you can just build an encoder model. The input will be just the input image and the first layer. I don't know if you can. But if you have the slides in front of you, so I mean, so I'm building a model. I'm building an encoder. I'm extracting this layer and I make an encoder using it. So the input will be an image, and the output will be this 32 values. So do you see now? I'm just plotting inputs, outputs. So when the input is 7, the output is 7. But remember, this one it's reconstructed using 32 values. So this is the code. So now the image, when we provide 7, this is for the test set. This one for the test set. The input is 7. The output also is, but it's a blurred image. It's because this one it's reconstructed using the small set of features. And now this is the code for building a classification model instead of working with BCA or instead of working with 784. I can work with those 32 values. So here I'm just building the encoder, right? So the encoder will be the input to the model and the first layer. How can I go here? This one. I cannot see my cursor. So anyway, I don't know if you can see it, but can you see the first line in your computer? So I'm just extracting the first layer as an encoder. So I build a model, in fact, after training your model, after training your autoencoder, you can just extract the first layer as an encoder, right? So the autoencoder consists of 2 parts, one encoder and one decoder. So I'm extracting this one and I want to use this one for dimensionality reduction, right? After training your model. So finally, we will have this one. This is the original image. This is the reconstructed image. This is the code. So now I can reduce this one from this higher dimensional space, which is 784, into 32 values, representing this one. And if you want to test it, you can just use this one with the decoder. So I build a model for the encoder and the decoder, and you can rebuild this image using the code. Correct? So it works as a PCA because we are now reducing the dimension from 784 into 32 values.
And it's the code that we use for training,
Mm-hmm.
the reduced code.
This one?
Yeah, the reduced one.
This one?
Yeah.
No, this is the one which we got in the bottleneck.
Yeah.
So this is the model for the autoencoder. The input is X, the output is X, and I just trained the model. Right?
Using the reduced features.
No. I just after training the model, you can just use the first layer as an encoder to reduce the dimension from 784 into 32. So this one it's generated
After training.
after training, right?
We use it for testing.
We use it for testing, use it for dimensionality reduction. We use this one for dimensionality reduction. So now, after training our autoencoder, I can just use the first layer to reduce the dimension from 784 into 32, and I can use those 32 for building a classifier. So now I don't need to keep this one anymore. I can just use only this one. Right?
Okay, I think I'm confusing maybe 2 concepts: dimensionality reduction and feature reduction.
It's the same, both are the same.
Okay, but then why should we?
Mhm.
Then why did we use all the features, the 784, to train our model and then to reduce them after finishing the training?
Yes, because they know BCA, we can use the BCA for the same task. So BCA, for example, I have 784 features, but it's too much. If I will build a model using those 784 neural network, for example, it will overfit. So I want to avoid this. How can we avoid this? By reducing the dimension of my features. I don't need to use all features. I just need to use a subset of features which are very powerful. So in BCA, for example, I can use BCA and I can select the first 32 principal components, and I use those 32 principal components for training a model, right? So we can do the same using autoencoder. But autoencoder, it's by training. It's like a neural network. It's not based on statistical tools, right? Because the BCA, it's based on statistical tools. But this one, it's by training. This one, it's data-driven. It's a neural network. And it's a neural network which looks like this one. So the input equal to the output. And once we train it, I can cut the first part and I can use it for feature, for dimensionality reduction, right? So now I can just clean that part here. So after finishing this one, I will just remove that part and I will build my model here. So now I will have my neural network here for classifying it into two classes. This one 0, this one 1, this one 9. I will connect this one to this one. And I will retrain my model, but I will not train this one again. Don't train this one again. We can
It's already trained.
because it's already trained. I'm using this one for feature, for dimensionality reduction. We will train only that part, not that part. Right? So because this is a model, I will not train it anymore. I'm just using it for transforming the input from this higher dimensional space into this lower dimensional space. And after that, I will add more dense layers here for decision making, for classification. When I train this model, I will not train those weights, because if I will retrain those weights, I will destroy that layer, because this layer has been trained already for dimensionality reduction. If I will retrain it again, I will destroy it. It's like transfer learning. In transfer learning, I can import a layer from somewhere and I can put it on my system and retrain part and keep part as frozen. Because I don't need to touch this one anymore. This one has been trained already. So now I need to just train the weights here, not the part. So now I'm sure that my system here will be simple because it has only 32 inputs. So maybe this layer also will be maybe 16 or 24. And this one will be 10. So now it's a simple model. It will not overfit my data. Right?
Okay, so what I understood is like this model is trained. We have a new data set, a new problem. We bring the data set, we use the first encoder, it will give us reduced features. And they will be, for example, we are going to move from 100 features to 50 features, let's say.
For example.
And from the 50 features, we will start training from there.
Yes, build a new model for
starting from there.
For solving the real problem here.
For solving
your problem, yes. But we trained the autoencoder because I want to reduce the dimension and I don't want to use BCA, for example. You can compare between BCA and this one. What is the difference? Is there any difference? Maybe using autoencoder will be much better, right?
For non-linear problems?
It's non-linear, correct? I mean, it's non-linear. When we use autoencoder,
BCA is that it makes the same number of principal as our features. Then we can choose how many to keep, how many principal components to keep.
Yes. Yes, if you will use the principal component, you will decide. You can do it and you can say, okay, I will try with 20. Next time I will try with 25. So maybe we have more flexibility, in fact, in principal component. But as you mentioned, because we have some nonlinear function here, nonlinearity in the autoencoder, maybe it will create more complex, it will be able to find the more complex mapping between inputs and outputs, and it will make something more meaningful, in fact, was a problem. So this is the results at the end. We will have some original images, right? We will have some code. We can use this code for reconstructing the image. We did that before for BCE. I remember we did the same problem here for BCE. We reconstructed the image using a subset of features, and it was similar, in fact, right? When we constructed an image, it has low resolution. So I just have it for all data points. So this is the original, and this is the code, and this is, remember, when it's black, it's 0, I guess. When it's white, it's 1, right? And when it's gray, it's number between 0 and 1. So now we can use this code for building a model for decision, for making some classification. This one, it's 2 layers, right? This autoencoder, we build it using 2 layers. There is also something called deep autoencoder. Deep autoencoder, which means we will just increase the hidden layers, number of hidden layers. Maybe your problem is too complex, so we need to build a model which is really more tough, more deep. So sometimes we need to go more deep. It's just simple, just adding more layers to have a deep autoencoder. Maybe your problem is more complex. If we're working with faces and stuff like this, or images of landscape or more complex images, maybe we need something more complex. So you can go more deep. You can even use convolutional neural network. I have no idea, I need to test that. So here I will increase number of layers, 1, 2, 3, 4, 5, 6 layers. So now we are going into more deep. I mean, those numbers, hyperparameters, you need to select, you need to choose by yourself, right? So I'm just giving an example by going more deep, and we can check the results. So I have here 3 layers for encoder, 3 layers for the decoder, because it's 6 layers. I mean, last time it was 2 layers. Now it's 3 layers for the encoder and 3 layers for the decoder. So we start here from 784, and we reduce it into 32. And we use those 32 for reconstructing again into 784. And I can build, after compiling, summarizing, training your model, I can just select that part for encoding, because I want to apply this one in my model for training, for other things. So I can just, how do you call it? Slice the model and take the first part for the encoder part for. Is there any difference? Maybe there is difference, maybe there is no difference, maybe the data set is simple. Maybe this deep autoencoder, we need to go deeply when the data is more complex and we have. So it's almost the same. There is no big difference, but maybe because the data set is simple, right? So this is so in fact, retrieve the last layers for the autoencoder. So I want this one for the encoding. So I build a decoder and I build an encoder here also the same. So I can take the first layer, 3 layers, after training your model, after training. I can just select the first 3 layers and I call it a new model encoder. And also the last 3 layers, and I can use it for reconstructing. Reconstructing is very important for denoising. So if I have too much noise and I need to reconstruct clear image, right? Maybe, for example, you can build a system for night vision, for example. I can train it to convert images which are taken at night time with, it could be something, an application like this one, right? So I build here a decoder. So I have already my autoencoder, we trained it and we finished. So now I have a decoder, right? So the output will be the output from layer number 3, decoder layer number 3. This is how we build it, right? And the encoder here, the input will be the input to the model, and the output from the layer number 3 also for the encoder, or layer number 6. So you can call this one layer number 3 or layer number 6 from the autoencoder. So I know today is more tough. So if you want to change the activation function, last time I used the activation function. Now I just changed the activation function into ReLU. Just try and retrain the model and test. Maybe the result here is much better when we use ReLU. Right? Do you see? It's more better in fact. When we use nonlinear, when we use ReLU instead of using linear function. So it's more clean in fact. Denoising.
We have a class.
Okay.
It's already 12:15.
Okay. So next time we can just go back again into this encoder because we need to work with the code. This is very important. In the slides you have all code in GitHub. just to go to it, please, and try to make some changes, right? And try to use it for autoencoder, for example, for those license plates problem, because we have a data set, we have images, so it should be possible to use autoencoder to improve quality. And imagine you are taking a picture at the raining. Sometimes when it's rain, it's really tough, right? You just get image with too much noise. So we can apply the autoencoder for removing this kind of noise from the images and improve the quality of the model. So you have all code in the slides. You have the code in GitHub, and it's working. So just please go to it and try to use it. And Tusen takk for it.
Thank you.
So please, online, do you have any questions for us today? We will stop here today, and we will start again next time. We didn't hear anything from people online, so in fact, I'm worried if. So please, you can just say anything, please, if you are online, still online.
Yeah, we are online.
Okay.
Following. Just that
Okay.
we need to go back and revise the slides once again to sort of like understand what's going on.
Yes,
And
please. Just,
about the assignment, so the deadline is today for the.
no,
car
we will
assignment.
extend it. No, for the home assignment, I will extend it to the maybe 2 weeks before the end of the semester. But
Okay,
please,
so
some
will
of you
this
have
be the
already submitted. So just this is one report. You can make 2 reports or 3 reports from the same project. So you need to use other tools. We will study deep learning next week or week after. So try to use deep learning. Try to use autoencoder. Try to imagine that you are collecting a data set with noisy stuff. You need to remove the noise using autoencoder. So try to use as much as possible from the techniques which you are studying. You are solving the problem now using shallow learning. Try to use autoencoder. When we finish also a deep learning, try to use deep learning techniques. So at the end, we need to have very good solution as much as possible. Go for any data set you want, but for the license plates, I'm interested in license plates, especially because we need to build a demo here in the lab. So your solution will be implemented here in the lab. We will have 1 week for presenting solutions and discussing solution. So we will have 1 day for people to present their solutions. And if your solution is really very good, you can get a prize. I will talk to Ricardo, maybe you can get Java code. So
this will the assignment. So it will be a group project. This won't be an assignment, but it will be a group. It will be a final project, right?
yes, it's a final project, but try to use as much as possible from the methods which we are studying.
Yeah, sure. Yeah.
Because you can make it simple. You can make it simple, but please try to consider noise. Try to use deep learning techniques. Try to fool the model by adding some those adversarial noise and stuff like this. So we try to make it robust as much as possible. And Ricardo is here. So Ricardo, please, we are discussing in a price because we have a project for.
Price.
So we need,
Okay.
so how much money?
We're gonna pay money for it.
So Ricardo is here. So maybe we can get maybe 2,000-3,000 from him. Or,
Maybe a car. Maybe an actual car.
what?
The actual car.
Maybe a real car.
Real.
Real car as a price.
A car.
Yeah, you are very ambitious.
GPU for doing what?
We have a project. We have student projects in the course. So we will have a presentation day at the end, and we need to get a prize for the best best project, best solution, second best solution
For the machine learning?
for the machine learning. Yes, and we will build a demo. So the demo will be here in the lab all time. So we will have a camera, we will have a system running in a computer connected to this screen. So
Yeah, let's discuss about it.
Okay.
If you all believe that this is something that might, give you an extra motivation, we can think about it. I mean, it's something that it's definitely a strategic area for the master program, strategic area for our department, for our faculty, and have this kind of activity might be useful. I want to discuss with Ibrahim to see how we can address that.
but just we will extend the deadline now. So just please spend more time working with it. Try to improve, tune it, and
Can all of us in the team work on the license plate to make it
yes,
instead of the model of the car, because it's similar?
yes,
Yeah.
yes. So just try to focus, but try to develop good solution. We will have the solution here. Thank you. I mean, we will have the best. We will have get this certificate. We will do it in the. In new graphics. We will have a good certificate. You will get a prize, hopefully. So we will have the solution implemented here in the lab, running all time, so people can test it and see it. So you will get very good credit from this project. Yes. Okay. So thank you very much for today, and please, keep in touch if you have any questions until we start again next week. Yes.
Thank you.
And we will go back for the auto encoder again next week. Yes. Thank you very much. All people are online, and we will meet again next week.
Okay. Goodbye.
Bye bye.
So you use this because we're showing this.
Yes. We need to get those cameras fixed.
Nej, så bara så talar jag med och så tänkte jag att jag först jag var ute så måste vi på det.
Because it says IT and IT.
Yes, the CC.
Ja, jag vill gärna samarbeta. Det kommer gå till. Ja, absolut.
Oh, well, so you give it to me.